Hello everyone, my name is Puriya Mohammadi. I'm a PhD candidate at the University of Utah Department of Civil and Environmental Engineering. This presentation summarizes the CTIPS research project. The project title is Data-Driven Inspection Planning for Utah Culverts using Federated Learning. This work was conducted at the University of Utah with Dr. Abbas Rashidi as the principal investigator. The main goal of this project is to explore how artificial intelligence and federated learning can support more efficient and privacy-preserving inspection planning for culvert infrastructure. Let's first explain why culverts are important and why their condition matters for transportation safety. Culverts are pipes or tunnel-like structures that allow water to pass safely under roads, railways, and embankments. Although they are often hidden below the roadway, they play a very important role in protecting transportation infrastructure. When culverts function properly, they help manage stormwater, prevent flooding, and protect the road structure above them. However, when culverts deteriorate or fail, the consequences can be serious. A failing culvert can cause road collapse, flooding, emergency closures, and safety hazards for drivers. The right image in this slide shows an example of when culverts did not work properly in Utah in 2023. Here you can see Payson Canyon Road completely washed away due to heavy rain. This is why culvert inspection and maintenance are so important. Agencies need to know which culverts are in good condition, which ones are deteriorating, and which one is close to failure. Now that we understand why culverts matter, the next question is what specific challenge does Utah face when trying to manage and inspect culvert inventory? Utah has more than 47,000 culverts spread across the transportation network. Inspecting and monitoring all of them on a frequent cycle is difficult, specifically when inspection resources are limited for Utah. Therefore, UDOT needs to make its culvert management program more efficient. The current approach is reactive maintenance, which means repairs only happens after culvert failures, and this can cause lots of negative costs for UDOT. So, our research team at the University of Utah proposed using AI and machine learning to predict the condition of culverts and prioritize the inspection for critical ones. As a result, we can avoid the consequences of failure of the culverts for Utah. For predicting the culvert conditions, we had to consider that different culverts may deteriorate differently depending on their attributes such as culvert material, age, size, environmental conditions around the culvert, and traffic exposure of the culvert. So a data-driven approach can be very useful, but only if we have enough data to train a machine learning model. And to do that, we need enough data. An actual culvert inventory for UDOT is very big, but the data that UDOT has is limited. This is the biggest problem that UDOT has for data limitation regarding machine learning. In other words, if we only train a prediction model using Utah's local data, the model may not learn enough patterns to make accurate and generalizable prediction. A natural solution would be to combine data from multiple state DOTs, but this can introduce another challenge, which is data sharing. Many state DOTs collect culvert inspection data and keep them in their inventory. Combining these datasets could significantly improve machine learning models. However, in practice, direct data sharing is not an easy approach. There are several restrictions here. First one is agency may have privacy, policy, or legal concerns about sharing raw infrastructure records. Second, different DOTs may use different data formats, inspection procedure, and different rating system. Third, even when agencies are willing to collaborate, transferring and centralizing raw data can be time-consuming and difficult to manage in terms of security risks. So the key question becomes how can multiple agency benefit from each other's data without requiring each agency to share its raw data? This is where federated learning becomes a promising solution. Federated learning is a machine learning paradigm that allows multiple organizations to train a shared model collaboratively without directly sharing their raw data. In our case, each state DOT can help its culvert data locally instead of sending raw inspection records to a central location. This makes federated learning specifically useful for transportation agencies because it supports collaboration while preserving agency control over local data. It allows agency to learn from a broader multi-state data set, but without the risks and barriers associated with centralizing all data records in one location. To make this clearer, let me walk you through how federated learning process works step by step in this slide. First, we create a unified format for our data feature, so each agency's data is mapped into a unified feature format. Second, we create a core ML model, name it initial global model, and share it with each transportation agency. Third, each participating agency trains the shared model on its own local data, and the raw data never leaves that agency. After local training, each agency sends only the model parameters or model updates to the federated server. After that, the federated server receives the model updates from each participating agency. It will aggregate them and send the improved global model back for the next training round. Over time, the global model becomes stronger because it learns patterns from all participating agencies while still preserving the privacy and control of each agency's data. This is the main reason federated learning is attractive for this project. It provides a way to overcome data scarcity while avoiding direct raw data transfer. With this framework in mind, we defined three research projects for our project. First objective was to test whether federated learning is feasible for culvert condition prediction when local data is limited. This is important because Utah's local dataset alone may not be large enough to support a highly reliable model. Second objective was to compare federated learning with traditional centralized machine learning approaches. We wanted to understand how close federated learning can get to a centralized model where all data is combined into one dataset. The third objective was to quantify the privacy benefit of federated learning. In other words, we wanted to evaluate whether we can still achieve strong predictive performance without requiring states to transfer raw culvert records. Together, these objectives allowed us to evaluate federated learning from both a technical and a practical transportation agency perspective. To achieve these objectives, the first major step was building a consistent data foundation across the participating states. An important part, as I said, is data collection and data preprocessing. We collected 8,240 total culvert data points from 6 states in the US. Different states use different culvert rating system, different inspection variables, and different formats for storing their data. Because of this, we developed a preprocessing pipeline to transform the data into a unified format. This included standardizing physical features, environmental features, and condition rating information so that the model learned from the different state datasets in a consistent way. This step was extremely important because machine learning model developed heavily on the quality of and consistency of the input data. Without a standardization, the model might confuse and do not learn the pattern for predicting culvert conditions. So before any modeling could happen, we had to make sure the datasets were comparable and could support both centralized and federated learning experiments. After creating this standardized data foundation, we developed and compared several machine learning models in our study. We compared four main modeling scenarios. The first model was Utah CL, which is a centralized model trained on Utah's local dataset. This represents the baseline scenario where Utah uses only its own available data. The second model was Utah Smooth, where we use Utah's data but applied a smooth technique to generate synthetic samples and address class imbalance. This helps test whether data augmentation alone can improve the Utah-only model or not. The third model was all CL, which is the last centralized model. It's a centralized benchmark model in our study. In this case, we merge all the data that we collected from all six states into one large data set. This model represents the best case performance scenario, but it requires full raw data sharing, which may not always be a realistic approach in transportation agency. The fourth model was all FL, which is our proposed federated learning model. In this scenario, all six states participate in training, but not raw data is sharing. Only model updates are exchanged for the core machine learning model. We use artificial neural network as a core ML model, and we handle because it can handle multi-class prediction, and also it can be implemented within federated framework easily. For the details of the model development and the parameters and hyperparameters, you can see the project report of our study. I put a QR code of this report in the last slide of this presentation, and you can scan that QR code and access that resource. Now, let's look how these models perform and whether federated learning was able to compete with centralized learning. These results that we got from our study shows that federated learning performed very well compared with other approaches. The proposed all-FL model achieved 80.4% accuracy, which is close to the fully centralized LCL model. This is an important result because centralized model requires all raw data to be combined, while the federated learning model does not need that. Federated learning also outperformed the Utah-only model and the Utah smooth model across the evaluation metrics. This shows that collaboration across states can provide meaningful performance improvements, even when collaboration is privacy preserving. Another important finding is that federated learning improved prediction for minority condition classes. This matters because poor condition culverts are often less frequent in the dataset, but they are the most important from a risk and maintenance perspective. Here we can take a look at AI collaboration metrics. Traditional Utah-only modeling protects local data, but it is limited because the model only learns from a small dataset. On the other hand, a fully centralized model can improve performance by using all available data, but it requires agency to share raw records between each other. Federated learning provides a middle ground. It allows agency to collaborate and train a stronger shared model, while each agency keeps its raw data under local control. This is the main value of the federated learning framework. It does not force agencies to choose between privacy and performance. Instead, it creates a pathway where agencies can improve prediction quality while maintaining control over their data. Beyond the technical result, it is important to understand what this means in practice for transportation agency. The practical value of this work is that it can support better inspection planning and asset management. This can also support proactive maintenance. If an agency can identify deterioration earlier, it may be able to repair or rehabilitate a culvert before major failure. Instead of relying on broad inspection cycles, agency can use predictive models to identify which culverts are more likely to be in poor condition. This helps prioritize inspection resources toward high-risk culverts. Another benefit is improved budget allocation and scheduling. When agencies have better prediction of culvert condition, they can plan inspection and maintenance activities more efficiently. And finally, the results from this type of model could eventually be integrated into GIS platforms or asset management systems that UDOT uses, allowing engineers and decision makers to visualize culvert risk and plan interventions more effectively. While these are immediate practical benefits, the long-term impact of this approach could be even broader. In long term, this project shows how transportation agencies can collaborate using AI without giving up control of their raw data. As more agencies participate, the shared model can become more generalizable and more reliable. This creates a scalable model for DOT to DOT collaboration. The same federated learning framework could be expanded beyond culverts. It could potentially be applied to bridges, pavements, rail components, drainage structures, and other infrastructure assets where agencies face similar data limitations. The broader impact is that federated learning can support a national or multi-state transportation AI framework, where agencies learn from each other while preserving privacy, data ownership, and local data. Of course, this work has also limitations, and those limitations help define the next steps for future research. First limitation is federated learning still requires some level of feature standardization. In this project, we only included features that could be standardized across the states that we selected for our project, which means some potentially useful variables had to be excluded. And in future studies, you can add these features and make a more robust ML model. Second, class imbalance remains a challenge. Poor condition culverts are usually less common, but they are very important for inspection planning. Future work should continue improving prediction for these underrepresented classes. Third, we use a basic federated learning framework, but more advanced algorithms such as FedProx and other personalized federated learning methods may further improve performance and reduce the gap between federated and centralized models. Fourth, this study included 6 states. Expanding the framework to include more DOTs could improve model generalizability and create a stronger national scale learning network. Looking forward, future research can explore federated transfer learning to handle non-uniform feature sets, apply the framework to other infrastructure assets, and develop real-time federated learning pipelines that updates as new inspections are collected. In summary, this project demonstrated that federated learning is a feasible and promising approach for culvert condition prediction and inspection planning. The proposed all-FL model achieved strong performance while avoiding direct raw data sharing. This means that transportation agencies may not need to fully centralize their data to benefit from multi-state collaboration. Instead, federated learning can provide a practical and privacy-preserving pathway for improving infrastructure asset management. The framework can be expanded to other infrastructure assets and additional transportation agency can be added. Overall, this work shows that AI can help agency prioritize inspection resources, support proactive maintenance, and make better data-driven decisions while respecting data ownership and data privacy. Thank you for watching this presentation. This project team at the University of Utah greatly appreciate the support from UDOT and CTIPS for funding this project. We also appreciate the guidance, feedback, and contributions of scholars in this research. You can access the project report by scanning the QR code I provided in this slide. Thank you so much.